So this video is going to focus on the derivatives of transcendental functions. So this is our standard D1 still, and we're on page 45. Okay, so the target is students will determine the derivatives of transcendental functions using the basic differentiation rules to determine the instantaneous rate of change. Okay, remember our derivatives represent our specific slope equation to the function that we are deriving. Okay, so we're going to talk about some of these transcendentals. We've already learned that the derivative of sine and cosine. So we know the derivative of sine gives us back cosine. Sorry, let's get a pen. Okay. Gives us back cosine, like I said. And of course, the derivative of cosine gives us negative sine. So all of our trig functions have a unique derivative. But remember, the transcendentals also include our exponentials and our logarithms. So we're going to talk about those specifically today. Okay, so the derivative of an exponential winds up being the actual exponential back times the natural log of whatever base our exponential has. So we derived and we actually did the proofs for sine and cosine. I'm not going to do the proofs for these, but I will post videos that show the proof if you are interested in that. We're just going to actually give the derivative this time. The one thing we want to remember is the fact that the a is a number, and that's important. Okay, so if we have a as a number like 4, 5, or 7, or -3, which it would never be -3, I guess it could be, yes. So if a is a number, that means our natural log of a is also a number. So that natural log of a actually acts as a coefficient to our exponential function, if we think about it that way. Now the derivative of e to the x, it is also an exponential, but it's a special exponential, the exponential involving e, but the derivative happens to be exactly the same. It produces itself back times the natural log of e itself, because that is our base. But there are two values for the natural log of, or for natural logs involving e that give us exact values. For instance, we know that the natural log of 1 gives us 0. We also know that the natural log of e gives us 1. And that's a special property, because if we think about it now, what we have here is that e to the x times the natural log of e, which happens to be 1, which really just gives us e to the x. So the derivative of e to the x is in fact itself. The slope and the y value actually have the same value at every single point on e to the x. That's a special property, and that makes the derivative really easy because the derivative doesn't really change the function at all, which makes it a really easy derivative to take because it's itself. So for example, on our a here, if I take the derivative of y with respect to x, well, that 5 is just a coefficient, so we've been bringing down coefficients and dealing them with when we need to, especially with cosine and sine, as you guys saw today. And the derivative of e to the x just gives us a basic e to the x back. So the derivative is in fact the same as the function. Easy derivative, I'm done, I can move on. Now the second one, that 4 to the x is the exponential, so I'm going to be able to use that rule above. But that 2 squared root of x needs to be rewritten because it's not in that power form. So we're going to do a quick rewrite to a positive 1/2. Remember, power over root there. So now everything's in a form where I can actually take the derivative. So I'm going to simply do that. dy dx equals, now the base of my exponential is 4. So that derivative of 4x is going to produce 4x back times the natural log of the base, which happens to be 4. And then of course minus, and then we're going to use the power rule that we've been using for the other one. So 1/2 times 2 gives us back 1, x to the negative 1/2 when we subtract 1. Last thing I would want to do in this problem is of course a quick rewrite. Don't want to have that negative exponent, and I don't want to have that fractional exponent. So we know to make that exponent positive, we're going to change its location to our denominator, and it's going to go back into square root form So our power of 1 and our root of 2. And then, of course, the 1 is going to remain. And there's our derivative. We're done. We can move on. The last one right here, if we take the derivative, bringing down the 7, and the derivative e to the x gives us e to the x. And then, of course, the derivative cosine gives us negative sine of x. And we're done. We can move on. So these are really simple derivatives. It's all about knowing what the derivative is, not being able to find it very much like the power rule. It's just knowing it. Okay. So exponentials have their own rules, as well as logarithms have their own rules. Now, the derivative of the natural logarithm winds up resulting in 1 over x. Simple derivative. The derivative of the natural log of x is just a simple 1 over x. We can use that property to actually find the derivative of any logarithm that we want with any base. Now remember, the natural logarithm is a special logarithm that always has a base of e, the number e. And then we have the log log, which can have a base of anything we want, any numerical value. Okay. So if we use that idea of 1 over x and the change of base formula, let's not do that. We can actually figure out what the derivative of log base a of x is. So I'm just going to scroll down. If we take the derivative of both sides, with respect to x, of course, I'm going to do one quick thing to my right side of my equation. I'm going to separate these into two separate fractions that are still being multiplied. Okay. And the reason I do that is to kind of pull out that natural log of a to be on its own, because we know the natural log of a is a number. Therefore, 1 over the natural log of a is a number. So really, it's that idea of that coefficient. I'm just going to bring it down to be part of my process, just like we did with the 7 and the 5 above. So I get that. And then from above, we know that the natural log of x happens to be 1 over x. And we're going to multiply them together. I always like to rewrite it. I always like my transcendental functions at the end, or transcendental functions values at the end. That way I don't make some computational mistake. So we get that idea of 1 over x times the natural log of x. But if we go back to the top up here, then you don't have to write this. Just kind of pay attention at this time. This, in fact, is the same formula. It just happens that, sorry, let me give myself more room. I've got arrow happy there. It just happens that we do have 1 over x, natural log, our base here is e. But as above, we said that the natural log of e is 1, therefore that's what produces that 1 over x. So they are still the same formula, it's just we don't really need that natural log of e there because it's just 1. Okay, so those two properties right there. Now if we go to the next page, we'll see two quick examples that we're going to do in pretty much less than a minute. Okay, the first example, again, we have that sum and difference rule, so we can take the derivative piece by piece, and that's exactly what I'm going to do. So we get that dy dx, 3 is a coefficient, natural log of x, if we take the derivative, we get 1 over x. We're done with that one. Minus, bring down the 2, the derivative e to the x is e to the x, minus 1/2, and the derivative cosine gives us negative sine. Remember that parentheses is pretty important. Okay, the last thing I'm going to do is just kind of clean it up. So 3 times 1 over the x, remember that's 3 over 1. Okay, so we're just going to multiply across. So really we get 3 over x minus 2 to the e to the x can be left. And then that negative 1/2 and that negative 1 as a coefficient of sine gets us positive 1/2. And then sine of x. And we're done. There's a derivative. Next one, to get the derivative, okay, again, 6 is a coefficient, I'm going to bring it down. And then that natural, or that logarithm with base 5 of x gives us that rule on the previous page. 1 over x times the natural log of the base, which in this case is 5. And then, of course, plus, and the derivative sign gives us cosine. Clean it up really quickly. Again, over 1, so we're going to multiply across. So 6 over x natural log of 5 plus the cosine of x. And we're done. So the really quick derivatives is just a matter of knowing it. We're going to do a lot of practice, and by the time we're done with that practice, you'll have the majority of them memorized, at least the important ones. So if you have any questions, come and see me.